Hi guys. So this is the second lesson I'm doing on integration by substitution. The first lesson that I did was, well, it is what standard level students are expected to know, and obviously higher level students as well. But for those substitutions, it's always in a particular form where it's a product of a function and the derivative of the inner function kind of thing, which, let me give you an example to explain what I mean by that. So say you have x times sine of x squared. You can dx, so you can integrate that by using integration by substitution, where you let u is equal to x squared, then du dx equals 2x, and these x's cancel, and it always works out quite nicely. It's not easy, certainly for standard level, but there's a process to follow, and it always kind of works out pretty much the same. Integration by substitution in higher level, which is basically this lesson here, is not quite as simple. However, if it's not of that form, they will give you the substitution, so that's at least one. That's a big plus, because you don't have to figure out what substitution to use. They will give it to you. In this case, they say let u equals x plus 2, and in this case they say let x equals a sec theta. So the first one is a fairly straightforward example. The second one is pretty much the hardest question I could find. I tried to find a really hard question. These integration by substitution questions can be really difficult. However, I actually find them really fun, and a lot of my students do too. That they're maybe not the types of questions you want to do under kind of high stakes exam pressure, but they're certainly fun to do when you're practicing at home. And obviously by doing that kind of practice and by enjoying doing them and practicing lots of different types of them, you get better and the exam becomes easier, etc. Okay, let's go straight into part A. So it says that u equal x plus 2, find the integral of x times the square root of x plus 2 dx. So we say let, over at the side, u is equal to x plus 2. That's very kind of them. And it's always the same. I differentiate this, still the same. Du dx is equal to, well, 1. So that's nice. And I can just go straight into du equals dx. So this becomes the integral of, now remember, I'm changing the x's into u's. So x plus 2 is u. Now I don't have the situation where this x is going to cancel nicely, as I said before, but I can still write x in terms of u. Look, let me draw a line here. If u is equal to x plus 2, then x is equal to u minus 2. So I can now write this as u minus 2, that's my x, times the square root of u dx. Now I should maybe have said at the start, the reason why I even need to use integration by substitution is because what could I do with this? I mean, I can't, like, you obviously can't multiply the x into the square root or anything like that. If I change this to x plus 2 to the power of a half, I still have the same problem. I cannot integrate it, so I have to use integration by substitution. But now you may say, well, hang on, do you not have the same problem? But no, I don't, because watch this. This is u minus 2 times u to the power of a half. Now this one, du, and I should have written that here too, actually, du, because I can change the dx into du because they're just equal to the same thing. But now, yeah, this one, I can multiply them out because it's just a u on its own to the power of a half. So u times u to the power of a half, that's 1 plus a half, which is u to the power of 3 over 2, minus 2 times u to the half du. Now I'm ready to integrate. So look, I've had to write 4 integrals before I'm actually going to integrate. So this is going to become u to the power of, so I'm going to raise the power by 1, so that becomes 5 over 2, and I divide by the new power, divide by 5 over 2, minus 2u to the power of 3 over 2, divide by the new power, 3 over 2. And then, let's keep going down. I then say this is equal to 2 times u to the 5 over 2 divided by 5. So because I'm dividing by the fraction, dividing by 5 over 2, I flip it and multiply, so it becomes 2 over 5. And then minus similar thing here. I'm going to flip this, which will make 2 times 2, which is 4u to the 3 over 2 all over 3. And look, notice I've forgotten my plus c. That's twice I've done that. Plus c. And then finally, he doesn't want it in terms of u. He wants it in terms of x. He asked me to find the integral of this. There's no u in that, so I need it in terms of x. But u is x plus 2. So finally, I can write 2 times x plus 2 to the power of 5 over 2 all over 5 minus 4 times x plus 2 to the power of 3 over 2 all over 3 plus c. Done. Now you may say, well, hang on, Mr. Flynn, is that the easy question? What's the hard question going to be like? Well, it's hard, trust me. But as I said, it's fun, and this is it. So, okay. Use the substitution x equals this to show that this equals this. Fine. So, I'm going to say, this is my answer, so I'm not going to use this. This is what I'm hoping to get at the end. I'm going to say the integral, well, let's write this out. The integral from a root 2 to 2a of dx all over x cubed square root of x squared minus a squared. So this equals, so what I'm going to do is, well, he tells me what to do. He says let x equal a sec theta. Fine. So x is equal to a sec theta. Now we always differentiate the substitution. So I'm going to say dx d theta equals this, the derivative of sec theta is in the formula booklet. It's sec theta tan theta. So that's a sec theta tan theta. Straight from the formula booklet. Fine. And I can rearrange this and say dx is equal to a sec theta tan theta d theta. Fine. Now, this I'm going to write down here is equal to the integral of, so instead of dx, I'm going to write, this is my numerator, a sec theta tan theta d theta. The denominator is going to be x cubed. Now, x cubed is this cubed, which is a cubed sec theta cubed, or sec cubed theta. Fine. Square root x squared. This is going to be a squared sec squared theta minus a squared. Okay, nice. So everything has been turned into theta, except, now this is to be really, really careful. These limits, move this over here a little bit. These limits here, 2a and a root 2, these are x limits. So these are the limits, these are x values, if you like. I want to find the equivalent value for theta, not the equivalent value, but I want to find what does theta equal when x equals 2a or when x equals root a root 2. Now, I have what x is in terms of theta, but let's find what theta is in terms of x. So x equals a sec theta, which means sec theta is equal to x over a. Now sec theta, remember, is 1 over cos theta. That's what sec theta is. So I can actually just rearrange this and say cos theta, so cos theta equals cos theta equals a over x. So when x equals 2a, I'm going to get theta when x is 2a and when x is a root 2. So when x is 2a, cos theta equals a over 2a, which is equal to a half. And when cos of theta is a half, theta is equal to pi over, let me get this straight, I'm visualizing my triangles, it's equal to pi over 3. And when x equals, what was the other limit, a root 2, when x equals a root 2, cos theta is equal to a over a root 2, which is actually equal to 1 over root 2. And again, visualizing my triangles, that means theta is pi over 4. So now I have my limits. It goes from pi over 4 to pi over 3. So look, for a root 2 to 2a, pi over 4 to pi over 3. So look, I'm not going to pretend this is easy. Every part of this, every little step I do is hard or tricky, but as I say, it's fun. Okay, so now I have my integral. Nice. This equals. Okay, I want to simplify this. Now, how can I simplify this? Well, look, see this thing here? This is equal to, well, it's integral of pi over 4 to pi over 3. And I'm going to write this out again. A sec theta tan theta d theta all over a cubed sec cubed theta. And then the square root. Now, the square root of, I'm going to take out the a squared, and I'm going to say sec squared theta minus 1. Now you might say, why have you done that? And how did I even know to do that? Well, look, again, that's what makes this tricky. There is an identity. So I'm trying to simplify all this. Now this looks horrible, but there is an identity that, well, if you remember your cos, let me just write it here. Cos squared theta plus sine squared theta equals 1. 1 plus tan squared theta equals, hang on, let me move that over here. Sec squared theta. So this is in the formula booklet. I like to just kind of derive these from there. I remember this one and figure these ones out for them. But look, if you have your formula booklet, you can go straight to your formula booklet. So I can actually say that tan squared theta equals sec squared theta minus 1. Now, yeah, again, you can say, how did I know to do that? Well, look, I kind of saw there's a, I don't know, I saw there's a sec squared theta minus 1 hidden in there. I knew that if I could change that to tan squared theta and then get the square root of tan squared, that would give me tan, and my tans will cancel, and I'll be left with this. So I could just kind of see it was going to work out quite nicely, but don't get me wrong, not many people would have gotten this right in the exam. So it goes pi over 3, pi over 4, same thing, a sec theta tan theta d theta. This now becomes this is a cubed sec cubed theta into, now watch this, this a squared, it's like a squared tan squared theta, but the square root of a squared tan squared theta is just a tan theta. Okay, hopefully that step makes sense, because now what I'm going to do is that cancels with that, and that cancels with that, and I'm now left with I am left with the integral from pi over 4 to pi over 3. A cubed is at the bottom, so you can actually take out that a cubed. So it's 1 over a cubed at the bottom. And then it's 1 over sec cubed theta. No, sorry, sec squared theta. So it's 1 over sec squared theta, which is actually equal to, let me write this step, 1 over sec squared theta d theta. That equals 1 over a cubed times the integral from pi over 4 to pi over 3. 1 over sec squared is actually cos squared theta, because that's, look, by definition, that's what sec is. Sec is 1 over cos, so 1 over sec is cos. 1 over sec squared is cos squared. And just when you think you're nearly done, you have to integrate cos squared theta, which actually isn't that straightforward, because we can't just integrate that straight away. We have to use the double angle identity. Now, straight from the formula booklet, we have cos 2 theta, this is our double angle identity, cos 2 theta, is equal to 2 cos squared theta minus 1. This is how we integrate cos squared theta and how we integrate sine squared theta as well, actually. Then I need to say cos 2 theta plus 1 equals 2 cos squared theta. And then cos squared theta is equal to this divided by 2, which is a half cos 2 theta. I'm dividing it by 2. Cos 2 theta plus a half. So this now becomes 1 over a cubed times the integral from pi over 4 to pi over 3 of a half cos 2 theta plus a half, and all of this d theta. This equals 1 over a cubed. Now, and only now, can I actually integrate it. So I'm going to integrate it. This becomes a half cos 2 theta. So this would be sine 2 theta, sine 2 theta, but I have to divide by 2 because of this 2, and there's a divided by 2 here as well, so I'm going to divide by 4, plus a half theta, just because that's a constant, a half theta. Close my brackets, and I'm going from pi over 3 to pi over 4. Now I can just sub those in. So I have 1 over a cubed into, let's do a big bracket, and I will do 2 smaller brackets here. So I'll sub in pi over 3. So that's sine of, this is going to be sine of 2 pi, sine of 2 pi over 3 all over 4, plus a half times pi over 3. Close this bracket, and I'm going to subtract. Now I'm going to sub in pi over 4. So this is sine, brackets, sine 2 times pi over 4 is actually just going to be pi over 2, and that's all over 4, plus a half times pi over 4. Close this and close this big bracket. Right, at this point I should probably look at what they want me to find, but let's keep going because this is fun. 1 over a cubed. Now, what is sine of 2 pi over 3? So every bit of this question is hard. So sine of 2 pi over 3, I like to use my cast diagram, C-A-S-T. So it's going to be up here. So it's going to be the same as the sine of pi over 3, and the sine of pi over 3 is root 3 over 2. So this is root 3 over 2, and it's divided by 4, so it's actually root 3 over 8, plus pi over 6. And then I'm going to minus, so sine of pi over 2 is 1, so it's minus a quarter, and then it's minus pi over 8. Okay, at this point I want to see what do they actually want. So they want, okay, I'm actually going to copy and paste this. Copy, because I want to see what I'm trying to get. So I want to turn this into this. That's kind of my answer. So here's my, okay, I'm getting there. Here's my a cubed, fine. So this is 1 over a cubed. And now I'm going to change that to a normal bracket. So I need a common denominator here, and that's 24. Nice, because that's a 24 here. So this is going to be, well, let's put the 24. Let's put it here for now. 24. And then this is 3 root 3. This is 4 pi, because this times 4, obviously. This is 6, and this is minus 3 pi. Okay, great, because I think this is now good. So this becomes 1 over 24 a cubed, open brackets. I have 3 root 3. 4 pi minus 3 pi is pi, so it's plus pi, and my minus 6, and there we go. And I'm even going to write QED to show, or just to say that I have shown that. Okay, fine. Look, no denying that's one of the most difficult questions I've seen on exam paper in any topic. But genuinely, as I said before, I actually quite enjoyed doing that, and I hope you did too. Definitely practice lots and lots of those types of questions. That's one example, and this is another example, but there's many different types of examples they can ask you, obviously. But the one thing to note is they always give you the substitution unless it is in that form that I showed you, where you see the derivative of the inner function and it's a product of that. Okay, that's it. Hope you enjoyed that very fun lesson. I will see you in the next one.